Welcome. I'm Attilio Castellarin, and I know already some of you, at least one of you. Instead, we didn't meet in the past. You're from University of Bologna? Okay. Ambiente Territorio? Okay. Please, tell me your name. I'll try to remember them since there are four of us. Maybe this time I'll succeed. Giacomo Mattei. Ah. We're just starting. Hello, welcome. So take a seat. There's no rush. It's the first class also for me, so I'm out of shape. You are Erasmus students?
Yes.
Okay. So I was saying that I am Attilio Castellarin. This course, Water Resources and Hydropower, is held this year for the first time. Previously, he had a different name with slightly different content. We decided to focus it more on water, surface water availability, and hydropower production. I will not be the only one teaching this class. I'll be teaching this class with Cristiana Bragalli. Our two modules will be in series, so until March, let's say, you will see me in the classroom, and from April on, Cristiana Bragalli. We have slightly different content. I'm an environmental engineer myself, and I was trained as a hydrologist. My background is on hydrology, and together we will see how to measure and predict, in case we do not have measurements, water resources availability, surface water resources availability, and also how to let's say, summarize the stream flow regime in natural stream and how to design, size the water availability potential for hydropower plants. We are trying to ventilate a bit this room because when I walked in, the temperature was unbearable. So I'll try to leave the door open. Let's see, please. This chair has wheels, so maybe I'm better off with this. I was starting by asking a name and a bit of self-introduction. Already forgot your name? Giacomo. Okay, Giacomo, and you're a student from University of Bologna? Sophia, and you as well are a student from the university, and you pick the exactly. So there will be a little bit of repetition because I have to harmonize the background at the beginning of the course, but then hopefully you see different things, okay? We will go more in detail since this is a master degree level. You are? Reza, okay. And you are, as a background?
My background bachelor is in civil engineering.
Civil engineering. You did hydrology?
Yes.
Okay.
Basics.
Okay. Mm-hmm. Matthew. Okay, Matthew. And you are from? I was trying to pronounce it the correct way, but difficult for me. Matthew. From France. Very good. Nice to meet you. As a background, you are? You have a bachelor in? And you did hydrology courses or not really? Okay.
And then
Say it again. Lille, okay.
From France, same
Okay, same university, same school. Good. Welcome. Good to see you. So I tend to record classes which you will be able to access afterwards through Virtuale. But this is not intended to empty the classroom. It's already not very crowded as it is. Classes are much better if there's a direct interaction with students, but you know, it may happen that you cannot attend the class, you fall sick, for a variety of reasons. I prefer to record my classes. I do it all the time and for all the courses I teach. I hope I will see a stable number of students. You're not that many, but also since we will have some practical activities, it's good that your number is small, so I'll be able to follow you closely. What are we going to see during this course? This course consisting of on both modules. We will address theoretically and practically some key elements that are associated with the design of hydraulic structure with a specific focus on hydropower plants. Of course, we will see theoretically, and then we will apply these theoretical elements, how you can, starting from observation of discharge, identify the hydrological design variables that are needed for sizing reservoirs, for example, and also, in case, and this is the majority of the circumstances from an operational viewpoint, in cases you do not have access to observation of discharge because there's no gauging station available, how to predict hydrological variables based on observation you collected elsewhere. We'll address this hydrological part, of course, in the light of sustainable development and climate resilience. So together we will see also how we identify environmental flows to preserve biodiversity, habitats, and ecosystem services so that we use surface water in a sustainable way. With me, we will focus mostly on hydrology. With my colleague, Cristiana Bragalli, you will address the technological part of the course. I have a few slides on my side. When you will start with Cristiana later on during the course, you will see the content of her module more in detail. Together, we will do some basic hydrology to level of your background and harmonize your background. I'll tend to be faster on these basic principles, but whenever I am unclear, you cannot follow what I'm saying. It's the first time you see these concepts. You would like to have some clarification, please stop me at any time. Don't be shy, okay? We have these opportunity to interact, so let's use them. Very good. So, we will start with some definition, general definition of fundamental concepts, for example, water balance at catchment level today. Then we will move to the hydrological variable we are interested in the most, which is surface water availability, discharges, and stream flows. We'll see how we measure them in a variety of systems, and then how to summarize this information for representing the natural stream flow regime. Meanwhile, we will see some practical application. First of all, we will address the use of standard tools in GIS systems in order to identify catchment basins and extract river networks from digital elevation model. You have already experienced in this area, or yes? So I can go home. And then in a programming environment, R, in R, we will see how to summarize this data, use this data to produce graphical representation of stream flow regime that can be directly employed for assessing, for example, the hydropower potential. More or less, this will be the content. We will focus together, you and me, on the hydrological component. Okay. Later on, as I was saying, the technological component will be taught by my colleague. Tools. We will use during this course some free and open software. Why free? You have questions? Please.
I never used the R, so it's
Okay.
something like that.
But don't worry, we will have also an introduction to R, so we will start together. We will use two softwares. One is R. R is a mathematical programming environment. The language it uses is an object language, very similar to MATLAB, for example, the environment, and the language very similar to Python, for example. If you use a large language model like ChatGPT, Gemini, you can easily grab a script in R language and have it converted by this artificial intelligence tool into a Python software, because the languages are very, very similar. Okay? We will use this software through a graphical user interface. It's called RStudio. You know this software, but I don't know about the other ones. Do you know R and RStudio? No? First time? I like this. There too? Zero? Okay. So R in itself, it's just a console, and you interact with it through text, command. You have a prompt and some command. Thanks to the graphical user interface, this RStudio software, the interaction becomes more natural, and the system in itself looks a lot like MATLAB, or at least the MATLAB I used to remember, because since the advent of R and RStudio, I entirely quit using MATLAB. You know MATLAB instead or not? A bit. What is the fundamental difference between R and MATLAB? R is a free and open source software. So together, today, as Unibos students, you have access to MATLAB for free. But tomorrow, as a professional, this availability will stop. And in order to use MATLAB, you will have to purchase a license. R and RStudio, they are open software. So they do have a license, but you are able to use them even as professionals, as engineers, provided that you acknowledge the utilization. That's it. Okay? The other advantage is that they are cross-platforms. So, regardless of the operating system you're using, Windows, a Mac, or Linux, regardless of the operating system, the look and feel stays the same. So we will be able to use this software in the classroom. You have a laptop, all of you? Okay, because not entirely sure you can use these software tools from a tablet. We will work in this room. We're not that many, as I was saying, so it will be easy for me to check what you're doing. And this year, this very room has been electrified, so you should have power sources, right? You do have. They work because it's a new thing, so you never know. The other software we will be using is QGIS. QGIS is a GIS environment. You have previous experiences in GIS environment. This software too is entirely open. So differently from ArcGIS, ArcView, from Esri, you will be able to use this software in your professional life tomorrow without purchasing a license. So during the course, I will try to illustrate theoretical concepts and then apply them in these two working environments through dedicated activities. Okay? For these activities, I will be distributing handouts on which basically all the steps are covered. Then the application will focus on, for example, performing the same computation, the same estimation, the same prediction on a different catchment, a catchment that is not illustrated in the handouts material and script material I'll be sharing with you. Okay, you have already QGIS installed in your laptop, all of you. It shouldn't be a big deal if we do not use the same version. If you want to refresh and update your installation, you may certainly go for it. It's recommended but not necessary because we will be using standard tools. You're looking at me, nodding, so you know QGIS where. Okay. So please, if you want to update your, a lot of chalk pieces, but all small. If you want to update your version, do not go for the latest, okay? Because it's the latest, it might have some bugs. You want to install the long-term release, latest version of the software, okay? Let me check if I can be more, if I can be clearer with an example. So if I go here, QGIS, okay, I would say that it's in English, so it's good. Download, skip. Okay, download before you start. It's all different. I should have done this before. I tried this, but okay. Here it is, 340. I think I don't have this version myself. So this is the latest release. Makes no sense to install this. This is instead a release for which the developers, let's say, ensure that you will have access to patches, bug fixes in the long run until a new LTR will be available. Maybe in the recent most one you have access to, let's say, very new tools, but perhaps there are bugs and they're not working properly. So much better to install the long-term release. Concerning R and RStudio, I understood that most of you never used it. So how do you install it? First, you install R, the main software. Once this is installed, you install RStudio, which is an empty box. It's just a graphical user interface. If you start installing RStudio first, then it will never work. It has to find R on your system in order to do work. So how do you install R and RStudio? I'll show you a couple of things today, but as you will see on our Virtuale page, there are indications, okay?
At the moment, it's closed. It's not available. The ones you like your page.
Yes. But it would be. It's okay. Closed because I want you to register with the password. So, okay. Good point, though. Well, first thing first, I wanted to show you how to access to R and install it. Is it sufficiently large? Let me increase the font a bit. Okay, R. So you start by installing R. I'm looking for letter R, and normally if you do so, the first link you find is this, R project. You click the R project, and then you see this page. A lot of information, but what you are interested in is this comprehensive archive, CRAN. So you go to CRAN, and you are prompted for a selection of a website. If you have a strong internet connection, you can pick whatever, okay? Even this, which is the base. If your Wi-Fi connection is so-so, then you look for the Italian mirrors. There are a couple normally. No, now there's just one. No, a couple. Milano and Padova. But the first server normally works beautifully. Instead, the Italian mirror, as you can see, okay. No, we got there. So here you find the three main operating systems, Linux, Mac, and Windows. You pick the one of your laptop, of your computer, and then you install the base version, okay? Base, not the contributor version, not the R tools, just the base version. You might also install the R tools. For some packages, what are packages? Additional libraries with specialized functions. Some of them we will be using. So in case you see you have difficulties installing a package, I will guide you through the installation of the package when we will need it. You have to install also this R tool if you are Windows users. You're all Windows users? Okay, Mac probably goes like for Linux, but see, you have a package here, and normally it's just the installation of this. In case you have problem, please let me know. Lilu, no. I was very lucky. And the equivalent of Matthew, which I'll never be able to pronounce. Say it again. Matthew. Okay. This is R. Okay, so you download the package for installing it or the executable for installing it on Windows. You install it. Okay, and only then you look for R Studio. So here too, R Studio Desktop. They recently moved to a different repository, this POSIT. So maybe the virtual page has to be updated. See, they stated two up front. First install R, then install RStudio. You click here and you can download the RStudio, which is also open source software. Okay, you install RStudio, then you should be all set. I don't think this week we will do a practical activity and introduction to the software, but between now and Wednesday, please try to install these software if you don't have it on your computer, and try to see if everything seems to be working fine. Okay, very good. I'll go back to the presentation. We are planning to have a nice field trip to Ridracoli. Ridracoli is a recent and rather large, according to Italian standards, dam. And we will have the opportunity to visit also the dam from a structural engineering viewpoint. It's a large dam. You have the main features here. For example, it stores 33 millions of cubic meters. The main purpose of the stem is to provide drinking water to Emilia-Romagna coast for the touristic seasons, during which the population explodes. This is the main purpose, but it is a multi-purpose reservoir, so also outdoor activities, hydropower production too. It was constructed recently, as you can see here, and we're trying to set up this nice filter. I'll keep you informed on this. In this link, you can ask you can access to the society. Unfortunately, it's in Italian. Romagna Acque is the society that manages the reservoir, and you have access to real-time data. For example, this is the water level in the reservoir. Of course, you can see it goes down dramatically during summertime because the main purpose is to provide summertime drinking water to the coast. Then it fills up across winter and spring. When the water level is up here, the reservoir is full. So if we were there today, it should look something like this. It's spilling water, overtopping, because the reservoir is full. Okay, so far so good. Am I understandable? You can follow? Okay. Teaching material. Okay. We use a lot the Virtuale web page for the teaching material and also for real-time communication. Okay, so it is important that you register. In order for you to register, I believe, to activate the resource. Okay. The only way to subscribe to this Virtuale page is through a password. Okay? The password uses a very difficult encryption system, so it is water, resources, and hydro power. Okay. Can you check if you can access the page? You see it? Good. Thanks a lot. What will you find on Virtuale? Of course, the slides, some additional studying material like scientific papers or textbook chapters, notes and report. Also, example and draft script for the practical activity are there. We will download them as we will need them, and we'll go through them together. And in case I modify a script, in case I produce some material during classes, I will upload the material itself in a shared folder. You can access through Virtuale. Now, let me check if I can do, let's say, simulate and access as a student. So the two of us see exactly the same thing. So news and announcement. It is very important that you subscribe to Virtuale, because if I have a last minute issue, I will contact you via email through the news and forum. If I have to share with you details for the field trip, I will do it through the news. Of course, if we see each other in classes, no problem. But if for any given reason I am not able to come at the time of the class, I will inform you through Virtuale. So it is very easy that you register. Then, there's not that many of you, but here it's an online form that requires 4 minutes to be filled, just to take note of your details, okay? So background, bachelor, name, surname, email address, and so on and so forth. See, so please fill this by the end of this week. Okay, it's not very complicated. Here, share notes from classes. This is the shared drive I was referring to. If I click, I end up in an empty folder. I will use this folder for uploading pictures, uploading modified R scripts that I integrated with some additional command, for example. And you will always be able to access it through Virtuale. Can you check if I gave the permissions correctly and you actually can access it? Yes? Good. Thanks. Accidentally I closed Virtuale. Okay, so as you can see, there are already some slides. Presentation is what we're watching right now. I will start with some introductory notion very, very soon. No other slides are available because I'm revising them a bit since the course changed from last year to this year. Then you have some indication for software installation, but it's mostly what we saw together, so there should be nothing, let's say, more difficult than that. There's a dedicated folder for introduction to R, but we will have a 1.5 hour to have at least the basic command to interact with R, and then we will follow scripts. So it should be easy. But when you have issues and problems, let me know, okay? As always. Then there are already 2 out of 3 practical activity I will present during the course. And this reports on practical activity is a repository. A repository where you are supposed to upload your reports. Reports you will do with me for module 1. I will give you indication on how to write these reports. I will show you also examples from previous years. To me, it is an exercise for you to write a technical report, which will likely be part of your job tomorrow as a professional and as a professional engineer. Okay? Then we have some references and additional material, but we will go into that when we will need it. Now, it is very important that I switch back to my normal profile, because otherwise Panotto fails recording. Okay. Through Virtuale, you will also access to the recording of classes. All good so far? Contacts. Here you will find telephone number and email addresses. Both of us, Cristiana and myself, we have offices in Via Risorgimento, so near Porta Saragozza. And during the teaching semester, we commute a lot between the two facilities. So, if you want to contact us for any problem, I believe that the email is the best way, okay? The telephone number is here, it's there, but I'm not in the office right now. Then I teach other courses, all here in Terracini, so telephone is not a big communication a good communication means, whereas email address is, email messages. Please do it, don't be shy. I prefer email messages to Teams, because Teams is my team profile is flooded by institutional chats, so it is very easy that I lose track of one-to-one chat messages like WhatsApp. Then you go down, I don't see you anymore. Whereas I am trying hard to keep my inbox tidy and organized, and so maybe I will not answer you on the very same day. Maybe it will require me a few days, but you are stay assured that I will answer you if you write me via email. And via email we can arrange meetings at any time. Okay? If you have doubts, I think I'm not very original saying this. If you have doubts, it's much better to solve your doubts here, because maybe the doubt originates from the fact that I wasn't clear. So your doubt is also shared by other students. So please ask questions if you feel that I'm not clear or something is. Don't go home with a question mark in the notes from a given class. Okay? Good. Very important. Course assessment methods. So, our exam is basically an oral exam. We will set several dates, starting from the end of the class. Since your number is not large at all, please provide us with indication in due course when you would like to have an exam, so that we do not set and open up exam dates that nobody likes, okay? In particular, for an Erasmus student, you have already a trip back arranged?
Yes.
When? End of June is great. Okay, no, because some Erasmus colleagues, sometimes they fly back to their home country even before the course stops. This is not good, because we cannot give exams online anymore. It's forbidden for University of Bologna policy. So all exams have to be in presence, unless you are either in a hospital or in jail. These are the two only options. Okay, so this could be tentatively the first date, just to have a place mark on the calendar, okay, the week after the course. But if you have already in mind a time period in which you would like to take our exam, please let us know. The exams are oral exams. You read point 1, may include a preliminary written test. This was used for large groups, but in your case it will be an oral exam. And it will be on the very same day for Module 1 and Module 2. So both of us, Cristiana Bragalli and myself, will ask you questions separately. You start with me, then you go to Cristiano, or vice versa. We'll ask you questions on the very same day, because it's one exam. And in her case too, the oral exam consists on questions on theoretical elements, things that we present during classes, okay? But also, in my case, it's very important, I will ask you to, let's say, defend your technical reports. The presentation of your practical activity, you will present as if you were a consultant showing the result of your investigation and studying work. How? You don't have to bring any printed paper. We will see a monitor, a screen. I will open up the PDF file with your reports and I'll ask you questions here and there. What is this diagram? What is shown here? How was this diagram created? What is the variable? What is its meaning? Why did you do this computation? So it will never be an exam on, for example, R syntax. I'm not interested into that because you can easily do the same steps in other programming environment, okay? So if you're able to follow my scripts and the practical activity, I am interested in the actual computation we perform, which you will have to describe in your own words. It's a very good training for you, because tomorrow this will be your work. Okay? Somebody gives you a study to perform, somebody asks you to design something, and then you will have to defend your output. So please, don't come and say on that very day of the exam, you know what, I did the practical activity 2 months ago because I did it right away as we were doing it in class, and now I don't remember it very well. Because you cannot do this as a professional. If you are performing a consultancy for an agency or a firm, you cannot say, look, I don't remember, it works, it's correct, it's fine, but I don't remember exactly how I did it. Okay, this is very important. Question on the exams. Is the exam clear for everybody? So oral, mostly will be oral exam. And please let us know your desired date. So we will open up on Alma Esami exam dates when you want them. And this is it. Questions? Our timetable works fine for you. You do not have overlaps. It's a problem because moving the schedule around will impact regular students. We will be recording. I'd love to have you in class, in particular when we do practical activity. It's definitely doable to skip some classes and look at the recording and ask me questions if you have doubts. But the way in which I designed this course works much better if you attend the classes regularly, unfortunately. You said 1 hour of the 2? Okay. I will try to tell you in advance when we are doing practical activities, so that of course you can bring your laptop, but also you are informed, so if on those occasions you can come earlier, because catching up, if we start something, particularly if we start something entirely new, catching up, it's difficult. And what else I wanted to say? That we start quarter past the hour, always. I will never start before 11:15, for example. Never. I will try to come here and set up everything so that at 15 we start teaching. Okay? Good. So, short break, 10 minutes. Good. You have questions? You don't have questions? Everything is clear? Okay. Short break and then we start with the theory. Okay, let's start today with some introductory notions. I believe that most of the things you're going to see today in the second hour of the class are things that you already know. In case it's not like that and you want to have some additional detail, please do interact. We will start with some notion on water balance. We will be focusing in particular on surface water balance. Together with me, we will be addressing the assessment, quantification of surface water availability. Then we will also mention, of course, watershed basins, but I believe these definitions are definitions you already have. I would like to start with this image. This image is a representation of the water cycle from USGS. You know what USGS is? The American Geological Survey. It is the equivalent in Italy of the system of Regional Agency for Environmental Monitoring, the ARPA agencies. I don't know how the system works in France. In France, you have a national centralized system for environmental monitoring, for example, rainfall monitoring, or you have regional agencies. Okay. We have instead Italy divided in administrative districts. Each one of them, Emilia-Romagna, for example, is one. Each one of them has an agency in charge of, for example, hydrological monitoring, and they are all, let's say, coordinated by a central national body. So we have ISPRA, is the central national body in Italy, and then under ISPRA there is ARPAE, for example, which is the regional agency for Emilia-Romagna, ARPIAV for Piemonte, like this. USGS instead, it's a national, let's say a federal institute in US in charge of environmental monitoring. They publish hydrological data. They publish data routinely of discharges in natural water courses, for example, but they also create some educational material. I think the website is very interested in if you want to have a look at it. How would you define hydrology? What is your definition of hydrology? What is it? Speak up.
The cycle related to the water, maybe.
It is the study, a scientific discipline that studies the water cycle, how water masses are exchanged between land, ocean, and atmosphere. But I would say this is very important, but from a quantitative viewpoint, because the objective is water management, for example, or water risk-related mitigation and management. So flood risk, drought risk mitigation and management. In particular, in Italy, hydrology is a discipline directly associated with engineering. So you become an hydrologist if you study engineering, civil and environmental engineering in particular. In other contexts, like in UK, for example, hydrology is more connected with geography. It's not like this culturally, for a cultural reason in Italy, where hydrology is associated with engineering. So this is a representation of the water cycle at large. This image is a rather recent image. They published it, USGS published it in 2022. Before, there was another image that is still present on their website if you go and have a look at it, and it's called Natural Water Cycle. What is the difference with this? The natural water cycle they had before included only natural processes. Whereas, what does stand out in this image? What do you see that stand out prominently in this image?
Industry,
Exactly. Urban areas, cities, so expansion of urban areas alter the soil properties. The runoff production is much higher. But also, look here, the agricultural production impacts significantly the natural water balance, right? Because you irrigate large crops. The flat portion of the region where you are right now, it's basically all agricultural, industrial agricultural land. It uses up a lot of surface water. In some cases, we deplete the groundwater for irrigating, like it is illustrated here, and this goes into evapotranspiration fluxes. So locally, the natural water cycle, which is the continuous exchange of water between ocean, land, and atmosphere, might be severely altered. And this is something we need to have in the picture, okay? Still, on the same resource, you have this very nice representation in order for you to have some order of magnitude of natural reservoir and natural water fluxes. Let's check the. It prefers Windows Edge is the name, which I don't like usually, which I don't use usually. Okay, so this is an interactive diagram. You have global pools. It means global natural reservoir where water is stored on Earth, and then you have global fluxes, which means movement of water at a global scale. Okay, so in my opinion, it is very, very interesting to look at the scales. See, here the scale is in cubic kilometers, and of course, the largest amount of water on Earth is stored in the ocean. If you put together all the water in ocean and deep ocean, it goes up above, so beyond 1 billion of cubic kilometers of water. That's the water stored in the ocean. If you click, this is an interactive diagram. If you click, you have the range, because what you see here are average yearly values, but some of these pools, some of these storing volumes may vary depending on how a particular year is from a climatic viewpoint. Of course, not that much the amount of water stored in the ocean. So you have a range, and it's very, very interesting to see at the span, the wide span of the scale. This diagram is in log scale. If I convert this diagram from log scale to a linear scale, you just see the water stored in the ocean, right? Everything else gets squeezed, basically undistinguishable. Only by putting the scale in log, you can have an idea on what is on average every year, the amount of water stored in permafrost. Okay? With and without ranges. So here you have also ranges. Permafrost, as you may see, varies a lot, because depending on climatic condition of each year, you may have more or less water stored. Here you have rivers. River is the smallest amount of water, but stored. Do you understand this difference? It's like taking a picture at a given year of the amount of water that is stored, trapped in river, torrent, and water courses. It's not a discharge, it's the amount stored in the river. If you want to know the global amount of water streaming through natural water courses, you have to look at, maybe I don't think I can increase the font. Let me check. A little bit. No, it stays the same. It adapts, but then it stays the same. Can you still read? Okay. If you want to see the amount of, the global amount of water flowing through the system of rivers, you have to go here. Stream flow to ocean. That is the overall amount of water that in a given year flows to ocean, and this is cubic kilometers per year. Okay? You can see also the range. As usual, you find a few additional indication if you click on each dot. So, Anthropocene, human in the picture, human in the global water balance. This is the global human water use. Of course, this number should be updated every year because the population is expanding. And if you look at this, it's overall 25,000 cubic kilometers per year. A huge amount of water, mostly used for what, in your opinion? Exactly, irrigation. And in fact, the image is quite illustrative. I have a question for you. So, this is human water use, right? And this is the stream flow to ocean, almost 50,000 kilometers. So twice as much the water needed. This is clean water, not clean, has to be proven. Not in many cases clean, but it is fresh water flowing through the ocean, and it's twice as much what we need as human population. So, since the runoff that flows to ocean is a renewable resource by definition, problem solved. At least with the current population, problem solved. We have enough renewable resource for anybody. There shouldn't be water conflicts, and we know there are, and we shouldn't be water bankrupt, as you. I don't know if you follow, but WMO recently published the fact that we are entering the era of water bankruptcy at a global level. So why is that? We have simply flowing in the rivers, we have twice as much water that we need. So why is water a problem?
There is no only humans that use water.
You think that's the only issue? These are average water fluxes per year, right? But seasonally, the water fluxes vary, and vary significantly. In some rivers in the south of Italy, there's no water flowing at all. So seasonal variation and distribution of the population versus distribution of surface water availability. They're entirely different, right? So a lot of population is living in regions that are characterized by water scarcity. Unfortunately, not everybody lives in regions where water is available. And sometimes water is present during some seasons and not present during others. So we need somehow to store the water in order to have it usable when we need it. Think about agriculture and these latitudes. We need water to irrigate in the seasons in which it rains the less. We need water to irrigate in summertime in Italy. And in this portion of Italy, natural streams are very low on water. This is why we need to have reservoirs. So this at global scale. Going back to the slides, some of the elements we already have pointed out in the interactive figure, and another representation of the water cycle, more quantitative. Here too, you have a global representation. In this case, the processes that are highlighted are mostly natural processes. Okay, you have a dam here, but that's the only thing that's there. Okay, no, this figure too should be updated and showing the impact of human water use on the global water cycle. It is mostly natural water cycle. You know all these, I guess you know all these processes, what they mean. Maybe interception is something you're not entirely aware of. What is interception? Do you have an idea? Mm-hmm. It's the rainwater that falls on vegetation, canopy, and that goes directly back to the atmosphere as evaporation. Okay, not to be confused with evapotranspiration. What is that? Evapotranspiration. It is the compound of evaporation, and evaporation is water that goes back to the atmosphere, for example, from water bodies or from the leaves of the plant, as we were discussing. And transpiration. Transpiration is instead a flux of water that goes back to the atmosphere, but due to the biological cycle of vegetation that gets water from the ground and then send it to the atmosphere through water vapor. So this image is interesting because there are a few numbers on it. This is the first example of water balance. We will not go much more into details in terms of water balance at the global scale, but you see some numbers here. 100. 100 is the precipitation on land. This is a global water balance that uses fluxes in terms of volume per year, setting to 100% the precipitation that falls on land. So if we suppose that on the system of continents, the precipitation, solid precipitation, liquid precipitation, yearly in terms of volume is 100%, then almost 70% goes back from land to atmosphere. Almost 70. Okay? 68%. And this is the complex of evaporation and transpiration from land. Then, still from land, a little more than 30% flows to the oceans. Okay? As surface flow. What happens on the ocean? Well, if the volume that falls of precipitation that falls on land is 100%, the volume that falls on the system of seas and oceans is 4 times as much. So 395, 400%. Why? Because on the ocean rains more, first. Second, because oceans cover a larger surface than land. Ocean covers 71% of the Earth's surface. So, because of these two reasons, on the oceans rains 4 times as much. This is balanced by the direct evaporation from seas and oceans. It evaporates even more because it's 428%. And what is missing here, it's moisture jet that from the ocean bring water vapor on lands where it rains. Okay? So this 32 that comes from the ocean percent and 68 that comes from land makes the 100% that falls on land. Sufficiently clear? Then, if you are interested in actual number instead of percentage, you can go back to the slide we just saw. It reports more or less the same numbers. And if you want an indication, this 100% is 110,000 cubic kilometers per year. Okay? We played a bit with hydrological processes, and we illustrated at a global scale and on a large time scale, 1 year, the water balance. Our problem as engineers is that we're not interested that much at the global scale. We have to address local problems, okay? And we're not interested as much in the situation, the average situation on a large time scale, 1 year. We are interested in local problems and time scales that are much smaller. If irrigation is our problem or hydropower production is our problem, we are interested at least at the seasonal time scale, for example. If, as engineers, we are interested in the problem of flood risk mitigation, then our time scale might be even hours. Okay? Very good. You've seen that equation before, right? All of you. What is that? That's the continuity equation. It's fundamental in hydrology. It describes the conservation of mass. It's written like that, but I prefer to see it like this. E as a function of time. What is that? The inflow, which is instantaneous. Okay? It's for a given instance. And it's, if we consider a control volume, overall the amount of water that inflows our control volume at a given instant, minus out. This is also a function of time, okay? And that's the complex of the mass outflowing the control volume at a given instant. This is equal to, if you are to describe that derivative there, how would you?
Volume of the system.
That's the volume stored in the system, which is a function of time, the volume stored in your control volume, which is a function of time, but inflows minus outflows, it's a variation of storage in time. So, okay, continuity equation, very important. This is the overall storage in terms of surface. If we look at water balance, overall storage in terms of surface water, groundwater, and water in the unsaturated portion. In order to explode a bit this equation for a system, a control volume, picture a piece of land like this one, and these are all the fluxes highlighted and the water stored in the different storages that might be present. Here, the title of this slide says open system. Why open, in your opinion? In the context of water balance, if control volume is open. What does it mean? It means that it exchanges water from outside. Okay, there are inflows and outflows from outside. I'm not referring to precipitation and evapotranspiration. These two fluxes, of course, inflow or outflow your system, right? I am referring, if I'm referring in hydrology to an open system, most likely to systems that receive surface stream flow from outside or receive an inflow groundwater system from outside, exchange water masses from outside, not in terms of, again, I'm saying this again, precipitation or evapotranspiration. So these are the different elements, inflows in the system. The natural inflow that is always present, even in closed system, is precipitation. The natural outflow, even in closed system, is evapotranspiration, so evaporation and transpiration. Then you may have, if the system is open, inflows as surface water or groundwater, and outflow as surface water or groundwater. Okay? This is in an open system. The equation I wrote here is instantaneous. Very, very often we will refer to finite time intervals, like seasonal water balance, so we will refer to season or monthly, okay, or a 1 year. This equation can be easily converted into the continuity equation for a finite time interval. Instead of this, you will have, I'm writing it like this, the inflow, but this has to be average inflow for your time interval of interest, minus the outflow, and this also is not an instantaneous value, it's a monthly value if you are looking into a month, if you are considering a month. And this is equal to the variation of the storage between the beginning and the end of the time interval divided by the time interval. Okay? Which you can write average inflow minus average outflow times the time interval is equal to the variation of the storage. Here, instead of inflow minus outflow, I have explicit term of hydrological fluxes. Okay? So, what you see P there is P, the amount of precipitation in the interval, which by definition is an in term, right? There's no precipitation that leaves your system. Make sense? Minus evapotranspiration. Evapotranspiration is an outflow. By definition, there's no evapotranspiration getting into the system, right? So this is just out. I don't have an in term. But the other two instead are overall outflows. This is conventionally, okay? You see minus Q here, but in reality, you should write minus Q out minus Q in. Because conventionally, the discharge leaves the system. Do you understand what I'm trying to say? You see G, the groundwater discharge. Same thing, conventionally it's a discharge, so it leaves the system. Is G out minus G in. And All these terms are either the total precipitation amount, the average evapotranspiration flux. This is rainfall, to have it homogeneous. This is rainfall intensity, so average rainfall intensity, average evapotranspiration flux, average discharge out, average discharge in, and the same for the two groundwater terms. Sufficiently clear? This, of course, you multiply by the time interval, and what you get is the variation of the storage in your system, which is open if you have these two terms. It's an open system from a hydrological viewpoint if you have Q in and if you have G in. Okay? Because those two terms are this. This is G in and this is G in, the inflow to the system. Normally, in hydrology, we do not refer to open system. Normally, we refer to closed system. System that exchange water with the atmosphere only, so in terms of precipitation and in terms of evapotranspiration. These systems are the watersheds, or the catchments, or the basins. These are all synonyms in English. Okay? Watershed, catchment, basin are synonyms. Normally, particularly in UK, a watershed or a catchment is the largest portion of land drained by the main river in the region. And then you have subcatchments. You don't have a sub-watershed, you have subcatchments. In US, everything is used more or less as a synonym. Basin and some sub-basins are used as synonyms. What is a watershed? The land area that channels the precipitation in terms of liquid precipitation, snow through snow melts, it channels in the river network, in the stream network, to an outlet, a given river cross-section, or to the ocean and the sea. Strictly speaking, in UK, a watershed drains the water to the sea or to an ocean. Okay, do you understand what I'm trying to say? Whereas subcatchment, we will see subcatchment later on a different slide. So, as you can see in this box here, it's often easier to visualize the concept by imagining that the topographical surface is completely impervious. It means completely impermeable. Okay? Do you know, there is written on the slide, do you know how this line is called? Exactly. It's the watershed or drainage divide. It divides the topographical surface into portions. If the rainwater falls here, it produces runoff here that will follow the steepest descent direction and will go to some river that is not in the picture. If the raindrop falls here and it produces runoff, then following the steepest descent direction, it will get to this river. Okay? Very good. Thank you. Erase this. It's not always that easy though, because the topographical surface is not impervious. Okay? Since it's not impervious, you might have a situation like this. A valley, a river, you want to identify the portion of topographical surface that collects rainwater and then returns this rainwater in the river. You have a mountain here on the side, and this mountain consists of fractured limestone up here. So a rock that is particularly permeable. And then some impervious geological formation right here. Right? So if the precipitation falls in a given point and produces runoff in this area, it will end up in this river. So this is the watershed divide for surface water. Okay. If you are on the other side of the watershed divide, this is the precipitation, this is the runoff. This runoff will end up in a different river, right? But then, some of the water also infiltrates, right? If the water infiltrates, it will end up in the groundwater. So, this is the water table and this is the groundwater. It will still end up in this river. But if the infiltration happens here, then this rainwater will still be fed to this river and not this. So you have, together with the surface watershed divide, you also have, in this case, a ground water divide. And the watershed, the ground watershed, is wider in this case than the surface watershed. Okay? Unfortunately, identifying the groundwater divide, which is needed for understanding the true overall watershed of a given river, is not easy. It's not that easy. You can do that with tracer, but there's a lot of uncertainty and ambiguity. So it is a problem, right? It is a problem because we have closed systems that we cannot accurately even identify. Situation becomes a bit easier when you are in regions like the one where we are right now, that geologically speaking are rather simple, meaning that our hills are mostly consist of geological units that have a very, very low permeability. So in these circumstances, it is possible to pretend to identify the watershed by considering the topographical surface as if it was fully impervious. But in many other cases, it's not a correct assumption, and this has to be kept in mind. Okay? Here you find a groundwater divide, a groundwater catchment that is dominated by the shape of the water table, right? This is the level where the water table is highest, and then it has some slope, and the slope is what determines the movement of the water. So from here, in this direction, the water will flow in this direction. This is an impervious geological unit, and here we'll have a spring out source of water. From this highest elevation towards the right, water will move in this direction. It will lose energy, so the water level will show an inclination like this. This is the true groundwater catchment. In many occasions, we will not be able to identify that, and we will simplify our problem by pretending that the topographic surface will be impervious. This is exactly what the tools we will see in the GIS environment will do. We will represent the topographic surface in a digital way, and we will extract stream network and watershed divide under this strong, in some cases, assumption. Here another image with some definition. the watershed, the main watershed is the largest closed system. If you look at river cross-section inside the stream network, these are sub-catchments. River cross-section are also called outlets, okay? A watershed or a basin or a sub-basin is identified only once you select a given river cross-section on the stream network. Good. Last slide on the water balance. Here you see the water balance in a closed system. Okay, a system that doesn't exchange with the outside water in terms of surface flux or groundwater flux. Is the equation different? No, because those terms, Q and G, were overall outflowing terms. The equation stays exactly as before. If you look at this equation, it's exactly the same. But because you don't see that, this is missing, and this is missing. Okay? And those are missing by definition, because you are considering a closed system. How do you identify watershed divides? You have to look at the topography. Okay? And in the past, watershed divides were identified looking at isolines, lines that indicate the same elevation. I believe that you saw these things already. Let me just quickly recall them. And let me know if what I'm saying is sufficiently clear. If you have on a map, a paper map, like the old style, old school. This is the peak, the summit of the mountain. And then you have isoline indicated points where the elevation is the same. It's very easy to draw watershed divides by looking at the curvature of the isoline. Watershed divides tend to intersect isolines where the curvature is maximum, okay? And normally you intersect isolines forming a 90-degree angle. Why? Because water flows in the surface according to the steepest descent direction. So a raindrop falling here will follow a steepest descent direction and will go in a river stream that is on this side of the blackboard. Here too, I am intersecting isolines with angles of 90 degrees. Whereas a raindrop that falls here will follow a different path and will go towards this river. If it's a watershed divide, the curvature looks at higher elevation. If it's a watershed divide, the curvature looks at higher elevation. It's like this. Instead, if it's an impluvium, where the river is located again where isolines show the highest curvature. But in this case, the curvature looks at lower elevation. In the past, watershed divides were identified in this way, but the process was highly subjective. Drawing a line is an exercise that I can do in a way, you can do in a different way, provided that we have exactly the same map. Nowadays, this is not the way to extract watershed divide catchment and subcatchments. This is performed using mathematical algorithm. that are objective. I run the mathematical algorithm given a digital elevation model, I obtain a watershed, you do the same, you obtain exactly the same watershed. There's no subjectivity in that case. Okay? But still, the process is this: identifying the steepest descent direction and detecting, extracting, or delineating, as the slide says, delineating the watershed. This will be the topic of a dedicated practical activity, starting from a digital elevation model, extracting the stream network, extracting the catchment that drains the water to a given river cross-section, perhaps where a stream gauge is located, and then also characterizing this catchment in terms of mean elevation, mean slope, mean annual precipitation. Okay? Good. This is more or less where I wanted to end today. I don't know if there are questions. I'll see you on Wednesday. Good.